Okay, so we're going to go and look at those final two examples and see what we can do with this equilibrium. So in this figure we have a ladder, has a length of 12 meters, has a mass 45 kilograms leaning against a frictionless wall. The upper end height is at 9.3 meters above the pavement. The pavement is not frictionless, so there is a friction that we're dealing with down here. We say that the center of mass is L3 from the lower M, so it's down here. We have a firefighter who is climbing that ladder until their center of mass is halfway up. And we want to know the magnitude of the forces from the wall and from the pavement. So here we go. So the first thing to realize is if the ladder is not moving, which really hopefully it's not, our net forces in the x direction should sum to 0. Our net forces in the y direction should sum to 0. So let's look at this first. So in the x direction, we have force from the wall. Now, if we scroll down a little bit, looking at our free body diagram, we also have that frictionless force, that unknown frictionless force. So the force from the pavement in the x direction, that should sum to 0. Those are the only two, right here and right here. Those are only two in the x direction. Now, what else do I know? Well, y direction. So I've got force of the pavement in the y direction. I've got mass times gravity for the ladder. I've got mass times gravity of the firefighter. Right? And those should all sum to 0. Well, there's two equations, but I have more than two unknowns here, and that is a problem. So let's look at the net torque. Now, we are going to need to work smarter and not necessarily harder. We need to get very clever in how we place our pivot point in order to calculate the net torque. So if I want to find the quickest way to look at my net torque, I am going to basically make O my pivot point. So if I look at O as my pivot point, what do I have? Well, I have mg acting a distance a/3 out. That's a perpendicular distance. That is going to make a counterclockwise rotation, so that would be positive. I have big mg that's acting based on this a/2. So that is giving me a good vibe here. And then way out here, I have the force of the wall times the height of the wall. That would be making it clockwise, so that's going to be negative. That should sum to 0. Now you may be saying, okay, but how am I going to get A? Well, our good friend Pythagoras. A is going to be the square root of the length of the ladder squared minus the height of the ladder squared at any given time. So we can find it that way. So right now, if I want to look at the force from the wall times the height, that's going to equal, well, little m over 3 plus big M over 2 times AG. So that means the force from the wall is going to equal 1/3 little mass, 1/2 the mass of the firefighter. That's over the 9.3 meters that this is. G is 9.8. And our A is going to be the square root of, we have a 12-meter long ladder. So this would be 12 squared. This is finding our A is going to be 12 squared minus 9.3 squared, because there's our H, there's our L. Plug all of this into my random number generator, and I'm going to get that this is about 407 newtons. I could then take this and get it back up here and find that our force P in the x direction, so our frictional force, is going to be about the same. Otherwise, how could that sum to 0? And then we can use our force equation right here in order to find what the force is in the y direction. Because force in the y direction is going to be little mg plus big mg. So that is just shy of 1100, well, just about 1100 newtons. It'll be a little bit over. Let's see, 1100, I want to say 46 newtons. It's about what that looks like. So here we have a safe that's hanging from a rope. We have a boom. So we've got a hinged beam with a horizontal cable. We want to know what is the tension in the cable. And then we want to find the magnitude of the net force on the beam from the hinge. So as a result of this. So we're going to come down here. We're going to start with that free body diagram as it's given. So just like in the past, we're going to look at the net forces and the net torques. The net forces in the x direction, we have as written FH minus TC. The net forces in the y direction, we have as written force vertical minus little mg minus the tension in the rope. Now these should sum to 0, so I should get that this is equal to 0 and that this is equal to 0. And then I could look at my net torque about 0.0. So if I look at my net torque about 0.0, I'm just going to write that there so we know where I'm starting at. I'm going to have the force applied and where it is applied. So I'm going to have tension in the cable times the lever arm. Now if you'll look, let me scooch this up just a smidge. Right here, that is the height A up, so I'm going to have that times A. I'm going to have the tension in the rope. That is going to create a clockwise motion, so tension in the rope. That is going to be times the distance B. That's how far it is out from the lever arm. Now what I'm doing is I'm giving you those perpendicular distances so we don't have to go ahead and do sine and all of that stuff. I'm just giving those to you. And then I've got mg. Now that distance is half, so that's going to be b over 2. And all of this should sum to 0. So if that sums to 0, the tension in the cable, which is one of the things I want to know, is going to be mgb over 2 plus tension in the rope times b all over A. Well, things we were given. We were given A and B. So we were given that, A and B. And we know that the beam has mass. We know that the safe has mass. Well, how can I get the tension in the rope? Well, the safe has to be stationary. So we could realize that the mass due to gravity of the safe is going to end up coming back up here as well. So the tension in the rope is going to be mass times gravity of the box. So TR is going to be 430 G. Now if I want to find the magnitude of the net force on the beam from the hinge, for that I'm going to start looking at torques. And I'm going to have to find both of these and use my good friend Pythagoras. So I'm going to come back up here and realize that the tension in the chain is equal to my horizontal force. So once I have it here, and this works out to be about 6,093 newtons. Got that. If I go up here, my force vertical is going to equal mg plus mass of the box times g. That's what tension in the rope is. So I've got both of those. So the force that I'm exerting on this is going to be the square root of the tension in the chain, the force horizontal that I found, squared, plus the vertical squared. That's going to be just about 7,900 newtons, give or take. So find your questions and let me know what they are.